All right, we're going to end with a couple of examples from the homework actually, and we're going to be looking at where functions may or may not be differentiable when we're actually given not just the graph, but we're given the function itself, the algebraic form of the function. So our first one here is going to be a piecewise function. So it's going to be f of x is negative 3 plus 5x for x is less than or equal to 1/5. And it's going to be 25 minus x squared minus 3 for x is greater than 1/5. And we want to determine where f is differentiable. Now, I've already kind of written out one of the things that we should just observe here if we're being asked to determine where f is differentiable is that it's a line for values of x less than 1/5, and it's a parabola for values greater than 1/5. And certainly when you think about, looking up above, the culprits of discontinuity are going to be sharp turns, corner points, cusp points, discontinuities. So certainly for values less than 1/5, the line is not going to have any issues. And for values greater than 1/5, the parabola is not going to have any issues. So all we're really going to focus on here then is, well, what's happening at 1/5 itself? And so the first thing we might want to think about is that middle observation up above, that where a function is discontinuous, it would be not differentiable. So often, and maybe you don't even write this out, but you're looking at it mentally first. So I would say the first thing you would at least kind of think about doing for yourself would be to determine and kind of test whether or not the function is continuous at x equals 1/5. Because if it's not continuous, so I'm even going to write that here, because if not continuous, then that is going to imply that it would be not differentiable. So that's why it's worth maybe just quick taking a look to see, well, does it just fail continuity? And this might be something you just kind of do mentally, and obviously if it fails, then you could write it out in more detail. But if you were doing your 3-step definition for continuity, first you would just decide step 1, does the point exist? And in this case, it does. We're looking for the or equal to, and it exists. Step number 2 is looking at your limit. And to look at a limit as x approaches what I always call that cutoff point of a piecewise defined function, we have to know to look at the limit from the left and the limit from the right and see if they are equal. Well, from the left is values that are less than, so that's the same kind of line part that we just plugged into. From the right is values that are greater than 1/5. So now we're subbing into the parabola portion here. And again, that comes out to be -2. So because these two values are equal, this tells us that our limit as x approaches 1/5 does exist, and it is equal to -2. So we pass there. And so our third step then is just observing that, the limit is equal to where the point was defined. So we are continuous. So now we're going to have to investigate a little more thoroughly. So I'll just kind of put in parentheses down here. So therefore, yes, it is continuous. So that didn't tell us anything. So in some ways, again, this really isn't necessarily the crucial work on this one, but it would have been if we had failed continuity, because if we failed continuity, then we could say it fails differentiability. But that didn't pan out. So what are we really looking at here? Here's the heart of what we need to look at then. We need to look at what is the derivative or the slope of the tangent line from the left, and then does that equal the derivative or the slope of the tangent line from the right? So this is where we're going to go back to our limit definition for the derivative at a specified point. So this is the definition from section 2.1, and we're going to look at it from the left, and we're going to look at it from the right. So the limit as x approaches 1/5 from the left of f of x minus f of c, which in this case is 1/5, all divided by x minus c. All right, well, from the left, this is, if you scroll back up and look at your piecewise function there, this is the line, -3 plus 5x. So the f of x from the left is -3 plus 5x minus 1/5 subbed into that. We've already done that arithmetic. That's -2, all divided by x minus 1/5. All right, so this is going to give us our limit as x approaches 1/5 from the left. Looks like in the numerator, we'll end up with 5x 2 minus 3, so minus 1, over x minus 1/5. Now, at any point here, if I was to try to evaluate this limit, I'm going to get my indeterminate form of 0 over 0. So I'm going to then do a little bit of reducing here by doing some factoring. And maybe it's not your typical factoring, but it's kind of mindful factoring that we're probably trying to reduce an x minus 1/5. And so if I'm able to factor out a 5 in the numerator, I do get this x minus 1/5 over itself. And so when I reduce that, I'm just left with the constant of 5. So the limit from the left is equal to 5. That's the slope of the tangent line from the left, the derivative from the left. Now, guess what? That's not too surprising. If you think about this, from the left, you have a line, y equals 5x minus 3. A line has a constant slope, it's 5. I just wanted to go through the algebra for you, but that's not terribly surprising in this case, so that kind of makes sense, right? All right, let's look at then the derivative from the right. So the derivative limit as x approaches 1/5, this time from the right, again, of f of x minus f of 1/5. So this is divided by x minus 1/5. This is now looking from the right, and as x is coming at 1/5 from the right, that is our parabola, 25x squared minus 3. So this is our 25x squared minus 3, but 1/5 subbed into that. Again, f of 1/5, that's -2. We did that up above, all divided by my x minus 1/5. And so let's do a little bit of simplifying here. So limit as x approaches 1/5 from the right. So we're going to have our 25x squared minus 3, minus 3 plus 2, minus 1. That's what I meant to write. So minus 1, all divided by our x minus 1/5. Again, if you were to try to do direct substitution, you're getting your 0 over 0. So we're going to need to, again, do some kind of creative factoring on this. And it's mindful factoring of really the fact that you're going to probably want to end up with a x minus 1/5 factor that's going to reduce. And there's kind of a couple ways. I mean, you could just break off one of these x minus 1/5 factors in the numerator and just do a little trial and error. Honestly, I think if we, another way this might look a little better, if we first maybe factor out 25, and then we would have x squared minus 1/25, and that's then the difference of two squares. So we now have x approaches, limit from the right, the x plus 1/5 binomial times the x minus 1/5 binomial. And so now we're able to reduce x minus 1/5 over itself, and reevaluating that limit, we have 25 times 1/5, subbing in 1/5 with the remaining x, plus 1/5. So that's going to be 2/5, and then the 5s would reduce, 5 times, so 5, 10. So this is going to come out to be 10. So the limit, or the derivative from the right, is equal to 10. So we just discovered that our derivative from the left is not equal to the derivative from the right. So these two are not equal to each other. So therefore, f is not differentiable at x equals 1/5. So if you're asked where it's not differentiable, it's not differentiable at x equals 1/5. If you're asked where it is differentiable, I can't remember which way I stated this question. So f is differentiable everywhere else, because we had a line and a parabola everywhere else. So it is differentiable from negative infinity to 1/5, parenthesis, union 1/5 to infinity. All right, one last example here. So suppose we're asked to determine whether the function f of x equals x to the 2/3 has a derivative at c equals -8. So this is the same thing. This is from the homework again. This is when you say has a derivative, this is the same thing as saying, is it differentiable? So has a derivative, this is the same thing as saying, is differentiable. So just so you're aware of that, those two are the same thing. All right, so once again, what am I really looking at here? I'm looking at, does the derivative exist at a specified point? So we're going to use our limit definition of the derivative, and since it's at a specified point, we're going to go back and use the one from section 2.1. So we're going to look at what is the limit as x approaches -8 of f of x, which is this x to the 2/3, minus f of this -8, so -8 to the 2/3, all divided by x minus that c, that x minus the -8. Okay, so this is, let's do a little bit of simplifying. So this we end up with in our numerator. If you think about -8 to the 2/3, that's like the cube root of -8 squared. So the cube root of 8 is -2, and then when you square that, you get 4. So this is going to be x minus 4 all over this x plus 8. So I have picked this one in particular to go over because having taught this course face-to-face before, this is often one that students would ask me about from the homework. So here's the thing on this one. First of all, if you were to try to do your direct substitution, you're going to have cube root of 8 again is 2. 2 squared is going to be 4. 4 minus 4 is going to be 0. And I dropped my negative. This was the limit as x approaches -8. That would still be 0 though in the numerator, over 0 in denominator. So we're in indeterminate form. Now, here's the thing. I'm doing this kind of mindful factoring approach on some of these. My goal here with a lot of these, because I have an indeterminate form, I'm kind of using my knowledge that I'm thinking that what I want to happen is that I'm going to want to be able to reduce this x plus 8. Well, in terms of factoring, x is just x to the first power. 8 does kind of look like a cube. And so 8 I could think of as 2 cubes, 2 to the third, 2 cubed, excuse me. And then we do have a formula for factoring the sum of 2 cubes. So if I could think of this as something cubed, we might be able to recall that we have a formula to factor the sum of 2 cubes. Like, let's use different variables here. Let's say I have a cubed plus b cubed. If you remember, that factors to a plus b times a squared minus ab plus b squared. that probably isn't a factoring pattern that you use as often as like the difference of two squares, but that is how we factor the sum of two cubes. So if I can now observe that I could replace x and think of it as x to the 1/3 cubed, because powers to powers we multiply, what that's going to tell me then is every place where I have an a, that's going to be like an x to the 1/3, and then every place where I have a b in my cube formula, that's going to be my 2. Oops, I didn't mean to highlight the b here before. The b is going to be the 2. And so this actually will factor according to a cubes formula. So you're probably thinking it's no wonder students have asked about this one before. So not only do we not often factor with our sum of two cubes, but it's also involving some rather unconventional terms when we start to look at like x to the 1/3 and writing that as a cube. So this is going to look like x to the 1/3 plus 2. There's my a plus b. And then my a squared is going to be x to the 1/3 quantity squared. I'll clean that up in a second. Minus the a times the b is going to be the x to the 1/3 times the 2, which again, I'll clean that up, and then plus the 2 squared. So I'll make that look nicer in the next step here, but just kind of, again, just factor for factor, what have I replaced here? And so it's all of those a and b terms just plugged into that formula. Okay. Well, okay. What does that do for me in the numerator then? Well, the numerator, maybe I should have started with that one. That one we actually could think of as the difference of two squares. So if we think of this x, if we think of this x to the 2/3 minus 4, okay. So if we think of that as being, obviously the 4 can be written as 2 squared, so that's pretty clear. And then we can rewrite the first term as x to the 1/3 squared. And then I think you're probably a little bit better, of course, with your difference of two squares. Okay, so then that's going to factor into your x to the 1/3 plus 2 times your x to the 1/3 minus 2. Okay, so that's, that's just your difference of two squares. So this is just factoring difference of two squares. All right, so this is a challenging one, isn't it? So let's go ahead now and say, aha, I can do some reducing of my x to the 1/3 plus 2 over itself. And so now let's see what we're able to do, kind of finishing this out. All right, so what do we have here? We would have our limit as x approaches -8 of, we're going to have our -8 to the, well, let's first rewrite it. If I'm subbing in, I should not. Here, let's first just rewrite this, since I do still have my limit notation there. So this is going to be my x to the 1/3 minus 2 all over x to the 2/3 minus 2x to the 1/3 plus 4. Okay, so -8 to the 1/3, so that's going to be cube root of -8 is -2 minus 2. And then in the denominator, cube root of -8 is -2, squared would be 4, minus 2 times, again, cube root of -8 is -2, so the minus 2, I'll write it here, times a little -2, and then plus 4. So we are going to have -4 in the numerator, and then in the denominator, it looks like we're going to end up with, what, 12 in the denominator. And so we are going to have negative 1/3. So this question was all about, is the function differentiable? I guess I now can actually say yes, it's definitely differentiable. So this right here, so this is equal to the derivative evaluated at -8. So because we are able to evaluate that limit, so I'll just say therefore, yes, f is differentiable at x equals -8. And in fact, the slope of the tangent line at -8 is equal to negative 1/3. So that's the last one for this section. So that was a meaty section.